Yay!
Yay! Okay, let's talk about an amazingly cool example of elastic collisions in the solar system, which is something that just about all interplanetary probes use now, at least most of them. And this is the idea of a gravity assist. So this is going to be a way of picking up enormous amounts of speed without having to carry fuel on the interplanetary spacecraft. The little probes that we send out, which is great, right? Because if you have more fuel, it's harder to launch in the first place. So this is a really neat way to pick up lots of speed without carrying fuel. All right, so let's see how it works because it's fascinating. Okay, let's take the first example. This is going to be the easy example up here. Just suppose we were able to come in. Here's our little green spacecraft. And there's a big planet, big M. And suppose we're able to just swing around the planet like this. The planet kind of catches the spacecraft in its gravity and slings it around the other side. So sometimes this is called the slingshot, gravitational slingshot. So what would happen if we could do this? This isn't realistic, but it's an introduction to the method. So what happens is that the spacecraft swings around the planet, and what we're going to say is that it just completely reverses direction. All right. So how we're going to analyze it is first, we're going to put ourselves into the frame of reference of the planet, into Big M's rest frame, because this is going to make things a lot easier. So how do we do that? In M frame, how do we get into that frame? Well, M is moving to the left with a speed Vm. So what we're going to do is we're going to add a speed to the right, V big M, because that's going to take that speed away then and make everything, make the big M speed 0. So what we're going to say is that in this frame, the speed, the initial speed of the spacecraft is just going to be the speed of the spacecraft that it had originally, and then we're going to add the M to it. Neat. So that way, we'll have the speed of the spacecraft in the rest frame of the planet. And adding the speeds should kind of make sense. If you think about going on a highway, if you are going one way and a car is coming towards you and you're both going at 60 miles an hour, in the frame of your car, it looks like the other car is closing closing towards you with the speed of the two added together, right? Like 120 miles an hour. It looks like the car is closing awfully fast. So this kind of makes some sense that we add those speeds together. Another way to think about it that we'll use in just a second is that I'm really it's subtracting the speed of Vm as a vector. Right, I'm adding the speed to the right, which is the same as subtracting the speed to the left. Okay, that might be confusing, but in the 2D example, that's going to be really what's going on. Okay, so if that's going to be the speed Vi prime is the speed of the spacecraft coming into the planet in the planet's frame, then it's pretty easy to analyze because it's an elastic collision. So remember, it's going to be sort of like throwing that ping pong ball at a bowling ball, and they collide elastically. So what happens to the bowling ball? Not much. What happens to the ping pong ball? If I'm throwing it to the right and it bounces off the bowling ball heading back to the left, it's just going to reverse its speed, right? So what's going to happen is that V final is going to be minus V initial, right? Okay, so now that that's V final, that's still in the planet's frame. So how do I get back to sort of the solar system frame of looking at this thing? How do I get back? Well, what I did to get into this frame was I added a Vm, so now I'm going to subtract it. So the final speed of the spacecraft in the unprimed, in the solar system frame, is just going to be minus Vi prime minus Vm. So I'm just going to subtract it to transform frames back out. I already know what Vi is, so let's plug that in. So this is going to be minus Vi plus Vm, and then minus Vm. So this is going to be minus Vi minus Vm, so minus Vi plus 2 Vm, right? Factoring out the minus sign. So here's the cool thing. Suppose Vi is 10 kilometers per second, sort of some typical speed of a space probe out in the solar system. So if that's the speed initially, and suppose a planetary speed out there, I don't know, the Earth's speed around the sun is about 30 kilometers per second. So I don't know, let's just say 20. Okay, so if our spacecraft is going at 10 and the planet is going at 20 in the other direction, what is our final speed going the other way? Well, what this is saying is that you take the 10 plus 2 times 20, so V final is minus 50 kilometers per second. Look at that. We've picked up 40 kilometers per second, an enormous amount of speed for free. Yeah, well, not really for free, right? Because what's really happening is we're stealing the energy from the planet going around the sun. We're stealing the planet's orbital speed energy. But the planet is so much more massive than the space probe. It's essentially free. We're picking up all this additional speed. So that's why this is a really valuable technique. Okay, so this is sort of an unrealistic example because, really if you dive in towards a planet at that speed, you're not going to come out in exactly the opposite direction. A more likely thing is what's going on down here. So a more likely thing is that you're coming in to the planet and then you swing around and you're going faster than the escape speed from the planet. So you're not captured in orbit, but you're going fast enough. So this is this whole trajectory describes a hyperbola. It's a hyperbolic sort of an encounter. So anyway, you have some velocity coming in and you have some velocity going out, and this is going to be in 2 dimensions now. This is going to be some vectors, right? So let's see how we're going to do it. Again, the easiest way to analyze this thing is going to be in the frame of the planet being at rest, and then we'll transform back out. So how are we going to do this in general? In general, I've got something like this. Let's draw these vectors out. So here's my, let's slide the vectors around like we can do. Here's my VI, and there's the VM, right? Let's look at this. This is going to be VI and VM. And what you do in general to transform frames is we subtract these. So, oops. So this is going to be this thing. Remember how vector arithmetic works. This is VI minus VM. And that is VI prime. That is the speed in the planet's reference frame. Notice that works. Look at the example we had up there. That's where VI was going only to the right, right? So if VI is going only this way, then if I subtract those two, I'm essentially adding it. And then we're back to what we had up here, right? So the general prescription looks like this. Generally, to get the speed in vector in one frame, to get VI in the planet's frame, this is going to be VI minus VM, like that. That's how we're going to transform frames. Okay, now in the frame of the planet, so now the planet's not moving, right? And this is an elastic collision. So if this is an elastic collision and the planet's not moving, remember what elastic means. The kinetic energies have to be equal, right? So what this means is that V initial in this prime frame squared, right? The kinetic energies have to be equal. The mass isn't changing. So VI squared has to be equal to V final squared for this probe as it swings around the planet. Okay, now let's use a little trick. What is VI squared? VI squared, these are vectors, right? So this is the same thing as saying this is VI vector dot VI vector, because that's really Vx squared plus Vy squared plus Vz squared. So this is Vi dot Vi I got to be careful and put the primes on there, right? This is still in the planet's frame. This is VF dot VF. All right. Okay, now let's try. So this is going to be true in the planet's frame. Now let's transform back. So let's see what this looks like from the solar system's frame point of view. Let's transform back. We know what VI and VF primed are. So let's write that down. So this means, let's see, VI prime. So this is going to be VI minus VM dotted with VI minus VM. And this has to be equal to VF dot VM. Oops, minus. Dotted with VF. Minus VM. Okay, so there we go. Now let's multiply that through and see what we actually get. And what we get is, this is going to be VI squared, right? VI dot VI. We're just going to kind of FOIL these things out. Minus 2 VI VM, and then times the cosine of the angle between them. The angle between VI and VM, we're going to call that the initial angle, right? We've got to, I kind of marked that down here. That's the angle between VI and VM. And then I have a plus VM squared. And then let's do it on the other side. So it's going to be VF squared minus 2. I'm going to write this in a slightly, I'm just going to rearrange this term just a little bit. This is going to be V M cosine theta final V final cosine theta final. Here's the angle between VF and VM. That's theta final, right? That's the final angle that the spacecraft is leaving. And then I have plus VM squared. Oh, look, I've got VM squared on both sides. That's nice. So that goes away. Now, look, I have, what am I trying to find? I'm trying to find the final speed of the spacecraft. Let's suppose we know the initial speed going into the planet or going into the planet encounter. I want to know what the final speed of the spacecraft is. So I'm trying to solve for this thing. I'm trying to solve here for V final. Well, what have I got? I got V final squared, and over here I have another V final with some junk in front of it. And then over here, I just have a bunch of stuff that I know already. These are the constants, right? The speed of the planet, speed of the spacecraft, and the initial angle of the encounter. I know all that stuff. So this is all a big constant. So look, this is just a quadratic equation, right? Here's my thing squared, and here is a constant in front of the linear term, and then here's just a big old constant. So here's what I'm saying. Let me write this as a quadratic. So this is going to be all the stuff on the right-hand side I'll keep on the right-hand side. So I have V final squared minus, that's why I wrote it this way, 2VM cosine theta final V final, and bring everything else over to this side. So this is going to be plus 2VI VM cosine theta I minus VI squared equals 0. There we go. So there's our quadratic equation where this thing is our B, right? And then this thing is our C. There we go. So let's just write down, the nice thing about quadratic equations is we can just write down the solution. All right, so let's just write down the solution. All right, so I've got V final equals, all right, what is it? It's negative b. Well, there's negative b. So this is going to be 2, 2 Vm cosine theta, and then it's plus or minus the square root of, all right, b squared, right? So this is going to be 4 Vm squared cosine squared. This is theta final. Minus 4ac. Okay, so this is going to be 4. A is just 1, so that's nice. I don't have to worry about that. Times c. This is 2 vi vm cosine theta I minus vi squared. There we go. Let's make a nice line here on top. There we go. Oh, all over 2a, right? Well, that's just over 2. So look, let me do this just to simplify it. There we go. I can get rid of that. I can get rid of that. And I can get rid of that. If I factor out that 4 and take the square root, then I have my final answer. So this, look, this is, and in fact, let me just make it a little bit better by, I'll make that minus and make that plus, and then I can take away the parentheses just to make it look a little bit nicer. And look, I think this is the general expression right there. Okay, so let's look at particular values. I looked up the values for the Pioneer 10 probe. The Pioneer 10 probe was one that was launched in the early 70s and visited Jupiter. And I think it was the first one to actually demonstrate how effective the gravitational assist was. So I looked up some of the numbers for that first encounter. And here we go. VI was about 9.8. This is all in kilometers per second. I'm running out of room, so I'll try to write a little smaller. VM, Jupiter's orbital speed is about 13.5 at that point. And theta I, the spacecraft was coming in at an angle of about 41 degrees, and it left at an angle of about 7 degrees. So it's not quite like the diagram that I have here. What really happened, it left on a sharper angle like this, and then it was actually coming in from behind the planet. So it was sort of coming in and kind of caught up to the planet and then came around the other side. So theta initial was actually coming, the spacecraft was actually coming this way towards the planet. So theta initial was less than 90 degrees. It was 41 degrees. Okay, so if you plug those things in, what you get is V final, the spacecraft was about, after the encounter with Jupiter, it was about 22.1 kilometers per second, which is about right. So this is what you get when you plug these numbers into the formula. And so the spacecraft picked up, it went from 9.8 to 22.1, which enabled it to go to Saturn, to hit objects in the outer solar system with no fuel expended, right? That's the magic. How do we know that this is sort of a complicated looking expression? How do we know that's right? What you can do is look at the limit. Look back at our first limit. Look back at our first easy example. It's not very physical, but we can look at it anyway just to see if the math looks right. What is our VI? What is our theta initial? For this example up here, I'm coming in this vector and the planet's moving at that vector. So the angle between those two is 180 degrees, right? So cosine theta I is a -1. And the final angle is 0, right? Because I've got the final vector here and the planet's going in the same direction. So cosine of theta final, well, theta final is 0, so that's just going to be a 1. Okay, so you can take the limit of the sort of complicated expression we have when theta final is 0 and theta initial is 180, and verify that you get the same thing that we got up there. So this expression has a good chance of being right. Okay, so this has been a really kind of a neat example of elastic collisions. All this is based on the idea that the collisions are elastic, that the no kinetic energy is lost. We're just stealing a tiny bit of orbital energy from the planet, but the planet's never going to notice. They're too busy doing other things, and they're just supermassive. So this is a really neat strategy that's still being used all the time to get probes to the outer solar system.